Just like with the other conic sections, I'm going to go through the information that's on your note sheet just so you become familiar with the terminology for the different parts of the graph. We'll transfer the information you will need on your graphic organizer and then go through some examples, and we're just focusing on writing the equations today. So, the formula for a hyperbola, and actually the definition, it's all very similar to an ellipse, even though the graphs do not look anything like each other. The characteristics, the equations are all very similar to what you have for ellipses. And you can have a vertical or a horizontal hyperbola, just like you have a vertical or horizontal ellipse. So it says here, similar to an ellipse, how a hyperbola is defined. It's the set of all points in a plane such that the absolute value of the difference of the distances from the foci is constant. So for ellipses, it was the sum of the distances to any point on the ellipse from the foci that was constant. Here it's the difference of those distances is constant. Not that you have to memorize the definition of what it is, but that is the definition or how a hyperbola is defined. So every hyperbola has two axes of symmetry. So an ellipse had a major axis and a minor axis. A hyperbola has a transverse axis and a conjugate axis. One does not have to be the longest. So for an ellipse, the major axis had to be the longer axis. Here, the transverse axis is the main axis, but it does not have to be the longest. So I'll talk about that more as we go through examples, but the transverse does not have to be longer than the conjugate axis. So the transverse axis shows, I guess, the orientation of the hyperbola. So this top hyperbola here is a horizontal hyperbola. It's opening to the right and left. So the transverse axis is the horizontal axis. The endpoints are the vertices. So it is a segment. Again, it's not the entire x-axis in that case. The vertices, not the foci, the vertices are the endpoints of that axis. So it's horizontal for a horizontal hyperbola, and then it's the vertical axis if the hyperbola is vertical. So it is the axis that connects the two vertices and goes through the center. And then the conjugate axis is the opposite one. So if the hyperbola is horizontal, the conjugate axis is the vertical axis. And the endpoints are the co-vertices. They are labeled here C sub 1 and C sub 2. Those are the co-vertices. And then for the vertical hyperbola, the conjugate axis is the horizontal axis. And I do want to point out everything that is dashed on these graphs. So that rectangle that you see, that actually the vertices and the co-vertices are on that rectangle. So that rectangle and then those two lines on both graphs, those are not actually part of the graph of the hyperbola. The hyperbola are the two curves that you see. That is the only part of the actual graph. All the dashed things that are drawn in, those are to help you create the graph of the hyperbola. We'll talk about that more when we actually graph them tomorrow. It does say the axes, transverse and conjugate, those are perpendicular at the center of the hyperbola. And then there are two foci, again that's plural for focus. There's two foci for a hyperbola. These always lie on the transverse axis, so you can see where they are. It's kind of like you have two parabolas again, and just like for one parabola, the focus has to be inside of the curve. So you see the foci are always inside of those curves. So they're past the vertices. And then it says the vertices, I already talked about this, are the endpoints of the transverse axis. The co-vertices are the endpoints of the conjugate axis. As a hyperbola recedes from the center, both halves approach asymptotes. So these dashed lines that are drawn in, I don't think they're labeled on here. We'll label them on our graphic organizers, though. These dashed lines are called asymptotes, and those are lines that a hyperbola or just any curve in general will never touch or cross. So the asymptotes are going to help us actually graph the hyperbolas, but you can kind of notice as the curves of that hyperbola extend outwards, they kind of follow where those asymptotes are going. They don't cross them, they don't touch them. And then it does say, the last paragraph, and we'll fill in our graphic organizers. As with ellipses, there's several important relationships among the parts of hyperbolas, two axes of symmetry. And then the values of A, B, and C are related by this equation. This equation is different than it is for ellipses. Some of you wanted to use this equation for ellipses, and then you found out your foci weren't graphing correctly. So this is the Pythagorean theorem this time. C squared equals A squared plus B squared. And that's because the foci have to be kind of on the outside of your vertices, not the inside like it had to be for ellipses. Okay, we're going to transfer this information to the graphic organizers and then go through some examples of writing equations of hyperbolas. And then you should have some time to work, ask questions if needed. So on your graphic organizers, we will start with the horizontal hyperbola. So if you want to make a note of the orientation, the top one is horizontal. Because the two curves are opening to the left and the right, they're opening horizontally. And I'll write down the standard form of this equation first. Like I said, it's very similar to an ellipse. It's not the exact same. So the standard form for a horizontal hyperbola is the quantity x minus h squared over a squared minus the quantity y minus k squared over b squared equals 1. So what you need to notice is with ellipses, we were adding the two terms together. With hyperbolas, you will have a minus sign in the equation. Either your x term or your y term will be subtracted from the other or will be negative. That's kind of thinking ahead to when we're just given an equation and we're asked to identify the conic section. If you see a minus sign in there, it's a hyperbola versus an ellipse. We will start out by labeling the center. So the center for a hyperbola, the center does not touch the graph of the hyperbola at all. But on your grid, it's where those two dashed lines, the asymptotes where they intersect, would be the center. And the center is the ordered pair HK. And then we'll label the vertices and the transverse axis. So the vertices then would be just like where you would see a vertex on a parabola. So each one of those curves has a vertex. And what I'm going to draw in, I'm actually going to highlight it in pink here. Again, the line segment that connects the vertices and goes through the center is called the transverse axis. And so I'm going to write in this box here, the transverse axis has a length of 2a units. And so it's up to you how you want to label this on your sheet. I highlighted it in pink, and then I'm highlighting transverse axis in pink, so I know that's what that is. If you actually need to draw an arrow to it to say it's the transverse axis, you do what you need to do. Grace? We did not for the horizontal hyperbola. The horizontal axis was the transverse axis. If it's vertical, then the horizontal is the conjugate. So the transverse will always connect the two vertices. Okay, so then we'll label these two vertices because they have formulas for their ordered pairs. I'll start with the left one. So this left vertex, the ordered pair to find that, the x-coordinate is h minus a. The y-coordinate is k. And then the right vertex, the x-coordinate is h plus a, and the y-coordinate is k. So A, again, is the distance. This is just like for ellipses. A is the distance from the center to a vertex. So if your hyperbola is horizontal, you would go to the left A units to the right A units to get your two vertices. And then we're also going to draw in and label the two foci because they're not actually drawn in for you on here. So the foci would be still in line with your vertices, but on the inside of each of the two curves. So if you just go out a little bit from each vertex and make a point so you can label those. And I'll start with the leftmost focus. So this leftmost focus has an x-coordinate of h minus c and a y-coordinate k. Is it not supposed to be what?
On a line, like.
It should be in line with the vertices. Do you mean like on the x-axis?
Well, like the focus is like on the bottom of the line, and I was like, I'm yeah, because I thought that like the focus would be like, I think.
It's in line with the vertices. I just didn't draw my center and vertex on the x-axis. I don't know if that's what you're talking about.
I think I made my highlights.
Okay. The rightmost focus has x-coordinate h plus c and y-coordinate k. So C, just like for ellipses, C is the distance from the center to either focus. And if it's horizontal, you go to the left C units, to the right C units to get your foci. Okay, and then we'll label the covertices. So now you see this box here. And I know this will make more sense as we're graphing them tomorrow. It didn't quite line up on your sheet where your vertices are on your curve. That should actually be touching that outer edge of your box. I know it's not. But the covertices then are in line again with the center, but they're up and down from the center. And they would be on that box. The vertices and the covertices, you use those 4 points to draw that box in. Again, we'll graph these tomorrow. That part will get cleared up tomorrow. But you'll have to draw in the covertices. And the end point, or those are the end points of the conjugate axis. So I'm going to highlight that here in orange. Again, connects the covertices, goes through the center, it's vertical. And then write that off to the side. The conjugate axis, and that has a length of 2b units. You need to draw an arrow to label it, that's fine. But even notice on this graphic organizer that conjugate axis looks longer than the transverse axis, and that's okay. The transverse axis does not have to be longer. For a hyperbola, A does not have to be bigger than B. B can be bigger than A for a hyperbola. So that part is different for hyperbolas versus ellipses. And then we'll label the two covertices. So the top covertex has an x-coordinate of h and a y-coordinate of k plus b. The bottom covertex has x-coordinate h and y-coordinate k minus b. So b again is the distance from the center to a covertex, just as with ellipses. The last thing I want to add in for this one is the asymptotes. So these are the two dashed lines that you see. There is actually a formula for the equations of those lines as well, and that formula can help you determine equations of hyperbolas. If you're given the graph of a hyperbola, you're given the equations of the asymptotes, you can use that to get your equation of your hyperbola. So I'm going to write in asymptotes is ASYMPTOTE, and then S. It's on your note sheet as well. But the equation for the asymptotes for a horizontal hyperbola, it's written in point slope form, not slope intercept. So it's y minus k equals plus or minus, because one of those lines has a positive slope, one has a negative slope, plus or minus, the slope is b over a times the quantity x minus h. We're actually going to be using the equations of the asymptotes today, so you'll see how those could be used to get the equation of a hyperbola. And then before we move into the vertical, if you want to make a note somewhere on your sheet, I'm going to write it up here if you wanted to write it in the margin, because it is the same equation for both of these. But it's different than ellipses, that c squared is equal to a squared plus b squared. So it is a squared plus b squared for hyperbolas. It's a squared minus b squared if you have an ellipse. But that is the same equation for both. So you can write it in both of these or just write it once knowing it's the same for both. Okay, so the vertical hyperbola now has all the same characteristics. So you can kind of figure out where to place things. We just have to label because the formulas are different. So this is now vertical. If you wanted to rewrite the c squared equals here, that's fine. The standard form for the equation for a vertical hyperbola is y minus k quantity squared over a squared minus the quantity x minus h squared over b squared equals 1. So the a squared and the b squared have switched, but what you need to notice is if it's horizontal, the term with y is being subtracted. If it's vertical, the term with x is being subtracted. That's the main tell as to which standard form you have. Okay, and then we'll start out again labeling the center. The center is at HK. And I'm going to, again, draw in my vertices. They're in line with the center. So now they're up and down from the center. And the length of the transverse axis, this is also the same for both. So if you wanted to rewrite this down here, you can. I'm just going to highlight it on this graph as well in pink. So I know on this one, the vertical axis is the transverse axis, but it connects the two vertices, goes through the center. And then I'm going to label the two vertices. So I'll start with the top one. So the top vertex has the following coordinates. The x-coordinate is h. The y-coordinate is k plus a. And then the bottom vertex, x-coordinate is h, y-coordinate is k minus a. And then I'll have you draw in again the two foci so we can label those. So one is above that top vertex, the other is below the bottom vertex, so inside of the two curves, still in line with the vertices. And I'll start with the top focus. Top focus has the x-coordinate h and the y-coordinate k plus c. And the bottom focus has x-coordinate h, y-coordinate k minus c. And then we'll draw in the two co-vertices and label those. So again, now to the left and right of the center, on the edges of that box you see dashed in, those would be where the two co-vertices are. They are the endpoints of the conjugate axis. So again, if you want to rewrite the conjugate axis formula below, you can. It is the same. I'm just going to highlight it in orange so I don't have to rewrite it. And I'll start with the leftmost one. So this is a co-vertex. The x-coordinate is h minus b, and the y-coordinate is k. And then the rightmost one, the x-coordinate is h plus b, and the y-coordinate is k. And then the last thing to label are the asymptotes, because the equations of the asymptotes for a horizontal hyperbola are different than they are from the vertical. So there is a different asymptote formula. So again, I'm going to highlight those. Or if you need to label the lines that they're asymptotes, that's fine. And then just write in here the formula for them. What is different with this formula is the slope. So everything with the form of this equation is the same except the slope is different. when you have a vertical hyperbola. So the asymptote formula is y minus k equals plus or minus, because again, one line has a positive slope, one has a negative. The slope is the reciprocal. It's a over b. And the times the quantity x minus h. Okay, so I know I've said this already, but there's three things up here in this box that are the same for both. If you wanted to rewrite them in here, you can. So the c squared equals, that is the same for both. The length of the transverse and conjugate axes, that is the same for both. So either just keep it written once like I have, or if you need to write it in both, that's fine. Any questions on what something up here says? If you didn't hear me, you can't read what it says, you want to make sure you have the correct information on your sheet. Okay. So then I only have 2 examples to go through with you of writing equations, and then you'll have time to work on some practice of your own. And actually, both examples give you a graph. But what I want you to realize is the graph is giving you information. So if you were just given a sentence that gave you information, it's much like how you've been writing equations of ellipses. You're kind of following that same problem-solving method to get the equation of a hyperbola. So if you look at example 1, we're given a graph. Write an equation for this hyperbola. You can see on the graph we are given the ordered pairs for the 2 vertices as well as the 2 foci. So we're given the vertices and the foci to write the equation of this hyperbola. First things first, just like with ellipses, figure out what standard form you have. Is it horizontal or is it vertical? We can see from the graph we're given that this is horizontal. If we weren't given the graph, I would recommend making a sketch to figure out if it's horizontal or vertical. So since I know it's horizontal, I'm just going to write down the standard form for a horizontal hyperbola. And again, just like as with ellipses, you need to find HK. So you need to find, well, I won't say you need to find the center. You need to find HK in some way, and you need to find A and B in some way. So ideas on where we could start to find HK. Think of how we found equations for ellipses. What? You just counted? Okay, yep, so the center, HK is the center. Center would be the midpoint of the vertices or the midpoint of the foci. You have midpoint formula, you have the graph, you could also just kind of count and figure out where it is. I'll use the midpoint formula just to show you that, but if you're given a graph like this, and if you kind of count your way to the middle, that does work in this case. So for the center, that'll give us HK. I'm going to use the midpoint of the 2 vertices. You could also use the 2 foci. So I have x-coordinates -2 and 8 for the vertices. So -2 plus 8 all divided by 2. And then y-coordinates, both are -6. So x-coordinate will be 6 divided by 2, which is 3. And y-coordinate will be -12 divided by 2, which is -6. So 3, -6 is the center, and that also gives you the h value and the k value. You might have also seen that k is -6. All 4 of these points have the same y value. The y value of all of those points is k when it's horizontal. Okay, then we need to find A and B. Let's start with A. Ideas on how to find A. Carter?
Maybe h plus a equals maybe 2 and 8. I think we can like perfect.
Yes. So if you're using, this is the only thing. If you're using the leftmost vertex, you would want to use h minus a. And then if you're using the right vertex, you'd want to use h plus a. Just to make sure your a value comes out to be the right sign. So if we used h plus a, I'm just going to make a note on here. The rightmost vertex, the x-coordinate is h plus a. So I know that h plus a should equal 8 in this case. And I can substitute an h now that I know h. So h is 3. 3 plus a equals 8. That means if I subtract 3 from each side, a is 5. Okay, so I have HK, I have A. I then need to find B. But if I'm given the two foci, what do foci, or what does a focus allow you to find? C. So in a similar way, again, I'm going to use the rightmost one. The rightmost focus has an x-coordinate of h plus c. I could also use the left one and use h minus c. So the 9 here would be in place of the h plus c. So I know h plus c equals 9. Substitute 3 in for h. So 3 plus c equals 9. Subtract 3 from each side. C is equal to 6. And then how do we find B? Yes. So c squared equals a squared plus b squared for a hyperbola. Substitute in your a and your c, solve for b. It will end up being the square root of c squared minus a squared. So I'm going to substitute in, if c is 6, c squared is 36. A is 5, so a squared is 25. So 36 equals 25 plus b squared. Subtract 25 from each side. And that gives you 11. I actually don't need to take the square root because b squared is what's in my formula. Here I know b squared is 11. If you take the square root, leave it as the square root of 11 so that when you square it, you get back to 11 and you don't have a decimal. Okay, so now I have HK, A, and B. I can write my equation. So it is x minus h is 3, quantity squared over a squared is 25, minus y, k is negative 6, it'll be y plus 6, quantity squared over b squared is 11, equals 1. Okay, so I know I've said this a few times already. Much like finding the equation of an ellipse, very similar process. Hyperbolas and ellipses have very similar equations, even though their graphs look very different. Okay, but if you struggled with writing equations of ellipses, the practice is what will help here. Okay, I have one more example, and this one actually involves the asymptote, so it's a little different. So example 2 still gives you a graph, but again, I want you to look at the graph to see what you're given. We are given the center. We are also given the vertices, and then we are given the equations of the two asymptotes. And we have to use that information to find A, B, and C. This hyperbola you can see on the graph is vertical. So again, if you weren't given the graph, you'd want to sketch the center and the two vertices, figure out if it's horizontal or vertical. I'm going to write down the standard form of a vertical ellipse, or vertical hyperbola, sorry. We are given on this graph the center, meaning we are given h and we are given k, so we don't have to find those. So I know, I'm just going to write this down though. I know the center is -4, -5, so that's my h and k. We can find a in a similar way for how we found a for the last example. We can use the two vertices. So if I use the top vertex, I can see on my graphic organizer the y-coordinate is k plus a. If I use the bottom vertex, the y-coordinate is k minus a. So I'm going to use the top one. So I know the -1, that is in place of the formula for k plus a. So I know k plus a equals -1. And I know k is -5, so -5 plus a equals -1. Add 5 to each side, meaning a is 4. So I have hk and I have a. I just need to find b. The only other thing we are given, or rather two things, we are given the equations of the asymptotes. So what's important about the equations of the asymptotes is the slope. Let's see, we have a vertical ellipse. The slope involves a and b. It is the fraction plus or minus, because again, one's positive, one's negative, a over b. And if you notice, the slope of your two asymptotes, one has a slope of 2/3, one has a slope of -2/3. So what that means is that from your asymptotes, the fraction a over b should equal 2/3. Or the ratio of a to b should be the ratio 2 to 3. I know a is 4, so I have 4 over b should equal 2 over 3. And you might be able just to see from this is a b here, you might be able to just reason what b is equal to. Otherwise, how do you solve this? Yeah, so this is a proportion, so you can cross, multiply those diagonals. I'm actually going to write this full thing out. This means if I do b times 2, so 2b should equal 4 times 3, should equal 12. So that's the 4 times 3, then I would divide by 2, so b is 6. Okay, so if you're given the equations of the asymptotes, you can use the slope to find a or b, but you would have to know one of the two. You would either have to know a or you would have to know b to be able to set up a proportion. So then I can write my equation. I have everything I need. So let's see, k is -5. So I have y plus 5 quantity squared all over a squared is 16. And then minus h is -4, so x plus 4 quantity squared all over b squared is 36. Equals 1. And notice here, I'm going to really stress this tomorrow because it's ingrained in your mind from ellipses that a has to be bigger than b. Notice a does not have to be bigger than b when you have a hyperbola. This a is smaller than b. That's okay. Hyperbolas don't have that same condition that ellipses do. But that's your equation.